Hello everyone, this is Professor DiPaolo, and I'm going to work through a problem involving confidence intervals. So this is going to be the one sample t confidence interval. So basically, for the confidence intervals, you need to know whether it's 99% confidence interval, 95, which is very common, 90. Uh, I've even seen 80% confidence interval. And basically, what it's saying is what is the range of scores, lower range and upper range, where we have a, say, 95% chance of locating the actual population mean. So we're using the sample to estimate or to guess the range of scores which contain the population mean. So what does this look like? It looks like this. Confidence interval, 95, right, is going to be equal to the mean plus and minus the t star value times s divided by radical n, which is the standard error of the mean. So the t star is basically the two-tailed critical value. So t star is two-tailed critical value at whatever the confidence interval is. So the confidence interval is 95, then this is going to be two-tailed critical value where p is equal to 0.05, two-tailed obviously, for whatever the degrees of freedom are in your sample. And the degrees of freedom for the one sample t-test is n minus 1. Right, so degrees of freedom here is equal to n minus 1. Okay? So we need to calculate the degrees of freedom, then we need to look up in the table what this is, and then we're going to find the two-tailed critical value. You're going to multiply that by the standard error here, and mean plus or minus that product, and then you're going to have a lower boundary and upper boundary. So let's look at some data, sample data here. So let me go into R to find sample data. So I have exam scores here. Let's see if I can copy that. So these are my exam scores. I'm just copying it from R, but I'm going to write it out here. So let's move this up a bit. So I'm going to write out exam, and these are my scores. I had just taken it from R where I had it stored. So 28, 29, 35, 37, 32, 26, 37, 39, 22, 29, 36, 30, sorry about the slanting here. So that's our exam scores. Now I need to find the standard deviation of these exam scores. So I have to first find the variance, which is going to depend on the mean. And so we're going to do that first. Let's find the sum and let's find the mean. So sum of exam, this way I don't have to worry about breaking out the calculator, is 388, and the mean of exam is 32.33. So this sum is 388, and then to find the mean is going to be the sum divided by n, which is 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12 here. So that divided by 12, and I did that in R here, it's 32.333. That way I don't have to do it on the calculator, do it on my phone or in my head, which is going to be rough to do that. So 32.333, double check that. Yes. Okay. Now this has a decimal. So if I were to do the deviation square method, it's going to be all decimals. So I don't want to do that method if I have decimals in my mean. So let's do the computational method. Remember that one? That's s squared is sum of x squared minus sum of x quantity squared over n all over n minus 1. Remember that one? That's the computational formula for the variance. So if I have decimals in my mean, I want to use this computational formula. So this is my exam, or this is my x score, right? So I'm going to have an x squared column, and we're just going to square all these values, and I'm going to do that for you in R. So I'll just do exam squared, and these are your values here. Let me copy that here. So these are my squared values, so I'm going to write them out. 788. And these can be laborious when you have big numbers here, right? So I'm not going to give you anything with big numbers, but I just so happen to have this problem pulled up and it had bigger numbers. So for the exam, you're going to have something very reasonable. I just happen to pick problems that are massive calculations for whatever reason. Although it's easier with, if I use R, it's much easier than using a calculator even, because it doesn't make, there's no data entry mistakes. So I'm just going to sum that up. Sum up exam squared. It's giving me 12,874. So let's go back. That's a huge value. So now I'm going to plug it into this formula. S squared is equal to sum of x squared, which is 12,874, minus sum of x, which is 388, squared over n, which is 12, over n minus 1, which is 11. So like I said, these calculations will be easier for the exam. Let's do 388 squared over 12. Gives me 12,545.33. 12,545.33 over 11. So now I have to do that. So let's do 12,874 minus 12,543.33. 330.67. All over 11. 330.67 over 11. Gives me 30.06 rounded. And then I will double check that in R. So let's do variance of this. So I'm a little bit off due to rounding error here, which is okay. There's just some rounding error. Okay, so that's our variance, and whatever I'm rounding numbers, there could be a mistake, you know, there could be a little bit of a difference, right? So now take the square root of s squared to find the standard deviation. So the square root of that was going to be 30.06 square root 5.48 rounded. And that might be slightly off from the exact probabilities here. Let's see. Yeah, so we're off by less than 2/100ths of a point due to rounding error. Which happens. I mean, you're going to get there's going to be rounding error. 5.47, I should say, is the rounded, not 5.48. 5.47. So let's go back to 5.47. There's our rounded answer. That's S, right? So square root of S squared is S. So now that I have that, I can get rid of these scores here. Let's delete that. I don't need any of that, right? So now we're going to go back and we're going to look at the formula here. So let's do the confidence interval of 95. So I'm going to need the I'm going to need the T star here. So let's do mean, which you have 32.33. So this is my confidence interval, plus or minus the critical t-value. So we're going to need the table for that. We have 11 degrees of freedom, and we're going to use 0.05 two-tailed because we're looking for a 95% confidence interval. So let's do table. We want the second row, which is two tails combined. We want that to be 0.5, and we want this to be 11. So it looks like 2.201. Remember, this is always a positive value. For a confidence interval, this is always going to be a positive value. 2.201. 2.201. So that's 2.201 here. Times the standard error, which is going to be S divided by square root of N. S is 5.47. Square root of N is a square root of 12. So let's bring that down here. It's going to be 2.201. So 5.47 divided by square root of 12. Let's do that in R. Square root of 12 is going to be 3.46. So this is like that. It's going to be 2.201. And now we're going to do this product. 5.47 and 3.46. This is giving us 1.58 rounded. $32.33 plus or minus. Now multiply these out. 2.201 and 1.58. $3.48 rounded. So now I'm going to have a lower and an upper value. So 3.23 minus 3.48. Is 32.33. Whoops. 32.33 minus 3.48. 28.85. Lower boundary, and then let's do addition. 3.23 plus 3.48. 32.33 plus 3.48, and we get 35.81. 35.81 right here. And you know, it might be off by a little bit of rounding error than the exact, because I rounded it multiple steps here, but it's close enough. It's within 1/100th of a point rounding. This is your confidence interval right here. So what this says is that there's a 95% chance, probability is 0.95, that the true population mean is between 28.85 and 35.81. Right? So we're 95% certain that the actual population mean is between these two values. And it's kind of the reverse of doing the t-test itself, where we're comparing it to a value to see if the value is different or not. Well, we can compare this interval to a value too. So if the null hypothesis is represented by a mean of 30, right? And this is the sample we have, and we're comparing the sample to the population, and let's say it's 30. Well, 30 is in this interval. So therefore, this sample would not be basically non-representative of a population with a mean of 30, because the 30 is in this interval. So in that way, if I was comparing this to a null hypothesis population with a mean of 30, I would say there's no significant difference. If I was comparing this to a null hypothesis population with a mean of 25, I would say definitely it's a significant difference, right? Because 25 is not in the interval, and therefore you would want to reject the null in that situation. So you can use these intervals and compare them with various population means to see does the sample, is it likely that this sample comes from that null hypothesis population, or does it not? And if it doesn't come from the null hypothesis population, then we reject the null. And so it's a little bit like working backwards. So hopefully that helps with the confidence interval. If you have any questions, you can either ask me in class, or we can do another one, or I can do it on Zoom. But it's pretty straightforward. The hardest part here is actually finding the standard deviation, finding the variance, because the calculation can be, look, in this case, the calculation was pretty extensive. For problems on the exam, the calculation will be very trivial. So it's more understanding the concept, and these are the steps, and hopefully that clears it up. So bye for now, and see you for the next problem set that I do.